Hi everyone, very honored to be the workshop. And my topic is general grasping, robot grasping with human life capability and high learning efficiency. I come from Shanghai Jiao Tong University. First of all, I will introduce the background. The advantage visual guidance grasping ability are recognized by early human and make tool to technically becomes possible and believe the facility the equation of human. However, the robots fall far behind human in visual guidance grasping ability. First of all, the contact model is still unknown, and the object shape is unknown, and the scene is cut. Variable or the mechanical design and make this make robot general grasping difficult. So my research objective is to make robot with human level general grasping ability. We emphasize the capability of the grasping algorithm in efficiency to graph learning. So my talk contains 4 parts. First one is the benchmark and how to benchmark grasping in computer. And the second one is methodology. The methodology we propose a new methodology to make the grasping in the deep learning is more easy. Another one is AnyDexGrasp. We hope we finally can grasp any objects in the general manner. The next one is we file can make the grasping adaptive to different different gripper. So this is my talk contains the 4 parts. First one, I will discuss the benchmark. As we know, we went with the discussion the grasping problem. We also need to make a good benchmark. But we always make in the real robots, so it's not efficient. We try to build a benchmark, make the benchmark the robots grasping problems more easy. For the background, human can easily use the parallel gripper for grasping easily that can detect, human can detect in the vision, detect the grasp pose in the very short time. But until the 2019, until the 2019, the robot skill as still take about 10 seconds to detect a grasp pose. It's also not very accurate enough for general object detection. For the general object grasping, in the deep learning time, the grasping pose detection is learned in the data-driven manner. And we collect a large scale of the data set and trained in a neural network. And this is our pipeline. And also we input the single view RGBD image. And we get some grasp pose detection. And finally, we output the grasp pose density. And we hope this pipeline is very general. Let's say we even for the unseat object, we can easily grasp to detect the grasp pose, and not only and it's very efficient. It's very fast in the short time, even can equal to human level to detect pose the grasping pose. So for the general grasping, first of all, we said we should build the data set, right? there are several important data sets for the grasping. For example, there's about 1,000, more than 1,000 objects and 2,000 objects in the EGAD, and even more data sets, about 8,000 objects in a bigger data set. So we also get some assumption. The assumption there is larger data sets, we have better performance, right? And with more and more objects should be, so this given this logic, we should collect more and more objects and to collect more and more objects. And we get so if you want to get more and more object, it's very difficult to collect in the real world. So we get the data label in the simulation. We have no choice to get the more data label in the simulation. And training the simulation and testing in the real time. Okay, this is also we think we have some assumption for this program. But if you think you are stand, but sometimes we should think more and think deeper. If you think you are standing strong, you should be carefully not to fall. Let us to review the assumption. First of all, we assume that once the first assumption is that the one larger data set equal to which collect more object, and the result means we need to so many objects we cannot only build in the data in simulation. And finally, the assumption 2, we can achieve the pretty good performance with a sync to real transfer. So this is some common sense before we start the research in this area. So we had to recheck and to review those two assumptions again when we begin for the general object grasping research. So let us review first. Assumption 1 is the large data equal to it means we have to collect more objects. This is first our assumption. What does the large data set mean for the grasping problem? Let's review this assumption. Okay, when we carry the general grasping, if we do not consider the task-specific requirements, the large data should provide more rich local geometry inside the gripper. This is not necessary to meet more objects. So we first review the assumption that is a larger data set is to mean that we need more objects. So let us recheck again. We to discuss we need two more objects to improve our data set or improve the performance. We should be analyze, should do some analysis on the grasp coverage analysis. We collect two data sets. One data set we called V1 and had about 40 objects, and the V2 we had 140 objects. So obviously the V2 is much larger than V1, and we want to analyze the coverage. We take a much larger data set to see is the performance for the V1 and V2. There we use the EGAD object data set. It contains over 2,000 program generate objects in simulation, and we have very compressed shapes. So we believe this data set cover a large amount or not enough local geometry to enable our coverage analysis. analyze, annotate the some graph posts in the training data, and for the testing object, if we find the similar graph post local geometry in the training set, we said okay, this is covered. This is covered enough the geometry. Given training data sets VA, V1, and V2, we integrate how well the graspable local geometries in training data sets can cover the test object sets. Okay, we can see this is V1 and V2. We know V2 is much larger than the V1 in terms of object number. And then we to check the how about the grasp coverage in the large data set, EGAD in the data set. When we uniformly sample the 1 million graphs and post in the each training object stage data training each training object, we show the coverage curve and in the training data set. We can see the object 1 and the V1 and V2 is very close. The performance is very similar. So we can make the conclusion that actually the object number is not an important factor for the coverage, the object, the grasping coverage analysis. When we sample the 4 million graph posts on each training data set, we show that the coverage curve is for the training set. Increasing the label density on training set is more important than the increasing the number for the training data set for training object. So we can see that this in this figure, the number, the sample, how the dense labeling, the label density is more important than object number in terms of the grasp the coverage analysis in terms of grasping coverage. So this will show some example that our training data training objects covers graspable local geometry in the large scale diversity EGAD object datasets. So we can answer this first assumption that the larger data set actually mean we need more object. Actually, I think is not necessary. We should include the density or the grasping label to make the coverage for the analysis, the coverage, the grasping concept. The result is we need so many objects, so we can only build a dataset in simulation. Okay, I think we can only limit or some or not so much object in the dataset. We can build the qualified dataset. So we answer the first assumption, and we answer the second assumption in the last the following the presentation. We know that we should densely sample the density. We get the density sample is more important. So now we build our benchmark for the generally grasping. The real world. So we have 3 requirements. The first one, we should real world perception. We adapt well to the real world and the low cost sensor. Of course, you can say we use very higher cost for expensive sensor, but we argue that we for the real world we more like the prefer the low cost sensor, and we should densely same label grasping label, grasping post annotation and billing label. And with the first one, we can argue a standard evaluation. We think the real a good standard evaluation should be low cost evaluation. So the research in different areas have proposed different solutions. how to give in a real perception and to get the dense grasping pose. For human dense annotation, we give you an image or 3D point cloud, and we choose label the different grasper, but it's sparse. It's very sparse. So we cannot get the dense pose. The second one is a robot correction. The second ones, but yes, we can do in the real perception, but it's more very expensive and inefficient. And the last one also we say the simulation, but simulation the population is not real, as we know, not real, and yes, we can get the dense pose, but it's not real. No existing methods can generate the dense X to Y pair. Let's say X is the real perception and Y is the dense grasping pose. This is our solution. We call the GraphStat 1 billion. We get the real perception and to get the grasping pose. First of all, we cache we get the 3D point called RGBD image, and then we have scanned the object model, and we can analyze the model we can analyze the grasping pose in a simulation work, and then we can repush the grasping pose in the real world. So it's very easy to make a very dense pose labeling. So my question you may answer that we scan all the object and then we make a digital twins in the real thing. Is very expensive. Okay, I think it's very expensive, but we have solution that. We have solution. We can 1 hour annotate. We can 1 hour annotate one thing with automatically system. That's we scan the object automatically, and then we push and pick and press paste the another very new things. So we can create one thing and get the post very easy, and you 1 hour to annotate, less than 1 hour to annotate one thing. In this way, we can collect a large number of the dense graph posts. Right? We compare with different data sets. How many dense posts in our data set, in different data set. We can find our data set is about 2 billion graph posts in our data set. Is largely significantly large than previous data sets in the graph post in terms of graph posts. So as we present the previous presentation, we say the dense graph post is more important. So we can build a new metrics in our dataset in this benchmark that inputs your real input in, and you can build your algorithms. You can divide different algorithms in your all-in-one algorithm, and we can propose the proposed estimation. You can get your proposed post estimation, graph post estimation, and we going in the simulation work to check the accuracy, and then we report the accuracy. Actually, we found the accuracy is very close to the real world grasping. So many people now have used this benchmark to test their algorithm, because we do not really use the real robot to test. Is very low cost, and we only to test in your computer. This is why I think this metric is maybe important for the scalable. Can be important for the general grasping if you want to test your algorithm very fast. So next one I will talk about the methodology. The methodology maybe we have very dense grasping pose, and then we discussed the new methodology. For the learning, now we have X and Y, right? X and Y. And the XY is the real perception, and the Y is the dense grasp pose, as we know. And usually people training a real network to approximate in the this pose. Usually people are training a real the neural network to approximate this pose, the pose process. Usually the standard that maybe previous doing is the previous method is to sample evaluation, and then for the random and heuristically sample grasp candidate and evaluate the crop local patch, right? Then we use the network to check this graph or not, yes or no. This is not end-to-end pipeline. And then the pipeline is very another, of course, another is end-to-end to pipeline and extract the feature in the whole thing. The sample grasp point is uniformly across the thing, and for the erase then all of them. Okay, this is two types of grasping methods. However, the number of negative grasp posts is 100 times larger than the positive grasp. In the thing, either random sampling and uniform sampling is very inefficient, is very expensive. And many computation research is wasted in the evaluating the potential negative grasp posts, right? So we propose formulate the grasp detection pattern in the different level. Actually, we have three levels. We let's decouple the parameter of grasping. X, Y, Z means that the location, or the location, or the position, or the gripper, and the YW and YVW as the parameter of the gripper, right? Actually, we use the Bayesian formulation. We can decouple this pattern. We want to get a thing and we to estimate the XYZ and RVW, but actually we can decouple. We decouple this pattern. First of all, we give me a thing, we estimate XYZ, that is where we can grasp. And then we give XYZ and thing, we estimate RVW, right? And we use the RVW, and then we add thing, giving a thing, the point y the probability for the XYZ, and the V point y the probability is XYZ, and the thing we estimate R and V. And then we have the R and V and XYZ, we estimate the Y, the Y. So it can make the pattern easy. We can see the three network. The first of all is the possibility where can be grasped, and the point the V white or the probability, and the angle white or the probability. Right? We can compute that all computed from our data set. We design an end-to-end neural networks to model those three terms or those three terms. First of all, we get in the possibility or where can be grasped, and then the possibility where grasp we can put as the input for the V point, and the angle point we can build an end-to-end the deep learning model, so we can end-to-end to get out the grasp pose. We design the end-to-end neural networks. During the inference, we free out the point and viewport the lower possibility in the east text. Our network can predict the thousand or the grasping pose in the two in very fast, about the 200 only very short time. This is our result for the predict the grasp pose. Another problem is sometimes we need we always need to rely on the data station, but when data station is correct, for example, the correct, how to do that? We automate data collection and create data with online to online article checking and collect the data or the pair or the RGBD imperfect data and the accurate the test information. Learning the mapping from the perceived RGB and imperfect data into accuracy depth. Optical-based object checking system. This is our optical-based object checking system and automatically data collection. This is our grasping system in the some transparent objects. Okay, next one is the AnyGrasping. We can learn the robot can learn the perfect effective and efficient the AnyGrasping system. And we found that we can use the small size of the data sets the object. We can get the pretty good accessory. For example, we compared with the DeskNet. We only use the 14 objects because we have them sampling, and then we can produce in testing in the large object. We also can get the pretty good result even with very small size object because we use the dense sampling. Any grasping is any grasping we can try in the any grasping comparison with compressions with human, we compared with paragraph, we can even we can defeat defeat the human. We can the accessory and the accuracy is better than human. So we recall the popular test. The assumption tool is we can achieve the pretty good in performance in the scene to real transfer. Now we have compression to use our method. We know the scene to real can work, but we do know how well work in compared to real data. This is use our methods to try in the real data and the synthetic data. We found the accessory is our accessory is significantly larger than the synthetic data. In dynamical environment, the graphing post detect in each frame would be switched down the local locations and orientations. We need to check in the object pose to contain the stable target, and so that the robot can move along the small trajectories. Most methods cannot guarantee the semantic coherence or the grasping pose. Even we use the nearest neighborhood or post evaluation. So we propose a detached association methodology. First of all, we define the grasping distance across things. This is our definition or the distance or the grasping here, and then we can propose the association in label through a corresponding metric. In this association metric, we can score between the two grasping poles in the calculation by the cosine, the similarity or their feature, and the score with here the grasping feature is learned through the supervised contrastive loss. This paper is assessed by Jiao. So let us see the result. the fish is unseat. We totally do not train before the fish. So we clean the fish tank for 5 times, and 40 fish can be grassed in total, and over salary is approached to 75. In the challenge in this challenges case, we argue again the fish and do not change the fish model before. So finally, we can file another test to AnyDexGrasp. When we at the beginning, human beginning with grasp case from terms or object and to thousands or the trying error. But until now, the robot still try to own the first 5,000 objects for the grasping purpose and mainly so successful in simulation. Though difficult to learn the different general grasping gripper. So many different gripper hand with content model is very not available, and hand model the kinetical is very difficult to know and time consuming in label the thing. We found a method can be able the robot to learn different gripper in different hand efficiently. Now our ongoing work can easily transfer to the two finger to gripper to the different mechanism gripper. We for the normal gripper on the about 100 fighting 100 fighting 100 fighting object, we can achieve over 90% success rate after 1,800 tries, and we can achieve even can achieve such a very high efficiency. For the fourth three finger, we only try 200 we can easy to get a high success rate. This is our opinion because this is coding, so later detail in this paper. This is we will submit this paper. To not help more so much detail. By conclusion, we grasp a perception system with human level ability with the gripper and successfully transfer the robust grasping ability to different robot hands with very high learning efficiency. This is our work about from benchmark to methodology and any grasping and AnyDexGrasp. Okay, thank you very much.